All right, so let's get started. This is going to be the January 2007 Regents. I'm going to review in this review session. And if you've done some of them, that's good. So we're going to go through this question by question. I'm hopefully going to go over not just the answers, but also go over the theme behind each question, because you're not going to see the exact same questions. You may, but the point here is that the same concepts, you will. So I'll try to teach the concepts behind the question. Please stop me anytime you have a question like, I don't get that, or something like that. So being crazy and going in order, let's start with number 1. And here we go with which subatomic particles are located in the nucleus of a neon atom. They could say any atom, all right? But what you should know at this point in time is that we're dealing with a nucleus of any atom, and of course the protons and neutrons are found in the nucleus. All right, I'm not sure why I'm writing so big here, but here we go. So protons and neutrons are the winners here. And you may say, well, how can I remember that if I have a problem? Well, you should know that the mass of the entire atom is due to the protons and neutrons for a couple different reasons. Number one, I would think you remember Rutherford's experiment. In Rutherford's experiment, okay, it was suggested and from his data collection, and he came to the conclusion that an atom was mostly empty space. Now, why? Well, because he shot something called alpha particles through. And these alpha particles, which you now know are helium nuclei, went directly through. So most of the atom was empty space. Very occasionally, these things deflected away, which told us the nucleus was positive, which is due to protons. And it also told us that the alpha particles, of course, are positive. Also told us that a small percentage of the overall space is this nucleus, and all the mass was located in this dense center. Someplace else you can go to figure this out, all right, is a reference table. And I like to use table O that most people don't use in this area. And if you look carefully, okay, a neutron has a mass of 1, and a proton has a mass of 1. So that's all the mass of the atom. Of course, a beta particle, which is an electron, they don't write it, has a mass of 0, but you should know that it's 2,000 times lighter. It does have some mass. So an easy question, some things that are definitely built into it. Rutherford's experiment, definitely. So number 1 is 3, easy stuff. Okay? Right. Number 2, the total mass of the protons in an atom of gold, 198. Well, they love to give isotopes. Now, you may say, well, how do I know this is an isotope? What's going on here? Well, why do they give me a number? Well, gold, if you go to table S, is AU. Right. Now, the 198, why are they giving me 198? Well, they're giving you the mass number, and there's a reason why they give you the mass number. And the reason is that gold, like any other atom, can have up to 20 different forms, heavier or lighter. So this is not the atomic number, this is the mass number, any particular type. Again, why? Again, I'm going to go through this why, because that's important you understand. If you go to your reference table, let's go here, and you go to table N. If you go to table N, you will see that they give you selective radioisotopes. Let's go see if I can find N. I'm not usually good with my, there we go, table N. And here they give you selected radioisotopes. Now why? Well, because some of them, like gold 198, gives off radioactive particles. So we want to know, if you've got gold, what type of gold you've got. So these are isotopes. So back to the question. All right, maybe. Keep doing this. So this is the mass number. So the total number of protons is not 198. Okay, it'd have to be whatever the atomic number of gold is. And if you forget, guess what? You have a periodic table in your reference table there. Let's go find our gold. All right, all that glitters is sometimes gold. In any case, the bad jokes will follow. So gold, if you don't know it's gold is AU, which is atomic number 79, you could also go to table S in your reference table, because in table S, they list not only the what? The elements, this one sideways, they give you the name for them, even though gold's not listed quite here. All right, so in any case, that being said, all right, atomic number 79 is what goes under gold. All right, and so that's why number 1 is definitely, 2 is number 1. All right. Again, not hard questions, but people fall for the 198. Is that's the number it is? No, that's the mass number. Why are they telling you? Because every element has a unique, like carbon 12 and carbon 14. They're both carbon. They're both atomic number 6. We don't have to write this number. Right. We can imagine it. Why? Because once you give me the symbol, it has to be 6. So it's redundant. By saying gold, we are implying 79. But I'm telling you which form of carbon, because this one is radioactive. They have different properties. Okay, so number 3. As always, I'll overteach every question. Right. Number 3. In a calcium atom in the ground state, when you hear atom, you say atom, I say neutral. Atom, neutral, atom, neutral. It's a poor dance party. Atoms are neutral. Atoms are always neutral. Now, if atoms are neutral, what does that mean? That means the protons equal the electrons. Now, I don't know if I need this, but that's what I'm thinking every time I hear atom. Electrons that possesses the least amount of energy are located where? Okay. Now, we have to understand that the farther that we go out from the nucleus, so here's our nucleus that's positive. Let's draw some shells here. They're not usually in circular orbits, but we're just going to use that analogy. So I've got an electron in the first energy level. We'll make this number 1. And I've got electrons in the second energy level 2. Now you should understand something. Electrons are negatively charged. The reason they stay next to the nucleus is because they are attracted to the nucleus. The protons that are positive, opposite charges attract, are keeping these electrons here. So in order for this electron to leap away and overcome this positive pulling force, it needs to gain energy. So you should know electrons need energy to jump away. Why? Because if an electron can exist farther away, it must have energy. It must have the energy to do so. So electrons that possess the least amount of energy are located in the first shell. Why? They're being controlled by the nucleus. Electrons that can exist farther away must have higher energy to overcome that attraction. So electrons that are in the last shells are the highest energy, which you should know are the valence electrons. Case in point, sodium is 2-8-1. That's its valence electron. In its third shell, this is the valence electron. And you learn that valence electrons have the highest energy. You should know that these are called the kernel electrons. These electrons, okay, do not have high energy. They're stable like the noble gases. So the higher energy ones that are farther away. So the least amount of energy are located in the first or the earlier shells closer to the nucleus. That's why number 3 is 1. Roger. All right, Roger Dodger. All right, number 4. Now, of course, the implications are that when an atom gets excited, electrons always gain energy to jump away. And then you should know, because they're excited and have higher energy, they don't last very long. When they jump back, they give off that energy in the form of light. They love to ask about these electron movements within the atom. It's a great part 2 question. Okay, number 4. Which group of atomic models is listed in historical order from the earliest to the most recent? Well, the most recent is called the wave mechanical model, or the electron cloud model.
So we could cross out 1 and 3.
You can cross off 1 and 3 definitely, because the wave mechanical model is in the middle.
Right.
Electron shell model is more of the Bohr, the circular orbits. Right. So yeah, 1 and 3 are gone. So wave mechanical models where electrons are acting as waves. Now, the answer is going to be 2, because the hard sphere model was the earlier model. They had no idea what atoms were like. John Dalton, suggested that atoms were, he was the first one to reinvent the idea of a modern atomic theory. And he said that atoms should be hard circles. Why not? Put your hand out the window, your hand moves back because something's hitting it. So why not be hard? He had no reason to think otherwise. So the hard sphere model was something that you would intuitively think atoms would be. It's just that it wasn't until Rutherford that we found that most atoms are empty space. Now, the electron shell model, this is the Bohr model. This is where the electrons went in circular orbits around. Okay, so that's what came next, and then the wave mechanical model. A little ditty here. Bohr had orbits for his electrons, and the farther away the electrons were, what? The higher the energy. He actually quantized the atom first. He was to say electrons exist in these exact quanta energy states, and to jump away, you need energy. To jump back, you release that same amount of energy. Because he was right, except his model was wrong because he can only, what, identify hydrogen, one proton systems. But he was right about these transitions. The wave mechanical model incorporated part of his word. Instead of orbits, where electrons exist, they call them orbitals. These are the places where electrons exist in the wave mechanical model. Any case, something you'll see. In the wave mechanical model, you should know the identifier is based on three things. You'll hear the word orbitals. These are places where electrons exist. Two, you'll hear of electrons acting as waves, not as point charges. And three, it's based on probability. So the wave mechanical model can be identified using orbitals, the place where electrons exist, electrons acting as waves, and we use probability where electrons are. Okay, just some things to think about as we go through each of these types of questions. Okay, isotopic notation for carbon-14. Well, if it's carbon, as I just mentioned, it's got to have a 6. Okay, only carbon has atomic number 6. How do I know? Well, if I go to my reference table, specifically my periodic table, I will see that carbon is atomic number 6, right there. So only carbon is atomic number 6. And they tell you atomic number 6 on the top of your table. They give you a little key here. All right? So say bye-bye to that. So now, if it's 14, why do they tell me 14? Because isotopes. Carbon can have up to 20 different forms, lighter and heavier. So carbon-14 is choice 4. The 14 is the mass number. Anytime they give a number with an element, they're telling you the mass number. They're telling you the specific isotope of that element, which is a heavier or lighter form of it. So choice 4 is the answer there. Okay? All right. Yeah. They're banging the same concepts over and over again. All right, here we go. Number 6. An atom of argon rarely bonds to an atom of another element because argon has, well, if you didn't know argon, you could check on the periodic table, and argon AR from table S, okay, argon is a noble gas. It's in this group 18, and you should know something about noble gases. They're stable. They have stable electron configurations, but you've got to understand in this course, stable means low energy. So, Mr. Stable, when I do it in class, I walk into class and I fall to the ground and I lay there. I'm not going to change my state because I have no energy to do so. I stay in that state. Your parents, strong influences, you're rocking your life. They're stable. They don't change, hopefully. Okay? So, these guys don't change because they have low energy. Their configurations, normally they have a stable what? Octets. Okay? So, back to the question. And argon rarely bonds to an atom of another element because argon has, okay, 8 valence electrons. Now this can really bother some people because you say, well, argon has no valable electrons, okay? But we say that argon has the 8 valence electrons to show that its octet is filled. And if it's filled, it's stable, or as some people would say, is happy. Because I'm happy? No. But the point being is that other elements like chlorine want to have 7. Chlorine has what? I'm sorry, want to have 8. Chlorine has 7. Hydrogen brings 1. And by sharing electrons, it feels like it's like argon. But this already has the 8, so that's why 6 is 1. It bothers people because people say, well, valence electrons are available electrons for bonding. Well, not entirely true. They're the outermost electrons. In the case of the noble gases, we'll say they have 8. And it's the only real answer that makes any sense there. So number 6 is 1. Number 7. Elements in a periodic table are arranged in order of increasing. Now, people will say atomic mass. They think as it gets heavier, it goes in order. And I understand why people might say this because, well, they remember that the periodic table was first made based on mass. And if you look carefully, it doesn't go in order of mass. The first periodic table did. Now, I don't know if you can see this, but cobalt's 58.9. Right. Nitrogen is 58.6. They're not going in order. In fact, in the old reference table, nickel was before cobalt until they discovered protons. And they put the entire periodic table in order of protons. So atomic number, the proton number, is how the periodic table is arranged by. Don't be fooled by the atomic mass. So, of course, it's the atomic number is the answer. Number 3, it should be an easy one. Okay, number 8. Which element is classified as a non-metal? Well, my friends in chemistry here, which one is a small atom that's above the staircase? You should know that the staircase, oops, not that. Here's my staircase. This is what separates. Astatine people believe it's also a non-metal. I'm sorry, it's a metalloid. So I just gave you the metalloids. This separates the big atoms from the small atoms. These are all big. These are metals. So everything to the left and to the right are your metals. And how do I know they're metals? Metals lose electrons. All of these become positive. You can't find a metal that becomes negative. They all lose electrons. These guys up here are your smaller atoms. They are so small they tend to gain electrons. So we're looking for something that's above and to the right of the staircase. Of course, the metalloids have properties of both metals and nonmetals. So back to the question. Who is a nonmetal? Well, silicon is on the staircase.
That's not it.
This is a metal. Beryllium's a metal to the left. Chlorine is above, so choice 4. If you don't know, check it out. Chlorine, here it is. Aluminum is a metal. Okay, that's why chlorine is the non-metal. All right, pretty simple stuff. All right, clearly chlorine is your answer, choice 4. Number 9. Some room here, maybe. Solid samples of the element phosphorus can be white, black, or red in color. The variations in the color are due to what? Okay, well, the key here is the element phosphorus. It's an element. It's not a compound. So it's just phosphorus. It's just phosphorus atoms. So I just have phosphorus atoms. But wait a minute. I have different physical properties. Now, this is an important, very important concept on the Regents. When you have different properties and you have the same element, you must have different structures. I say structure is king. You change the structure, you change the properties. So structure is king. The only way to have different colors is that these phosphorus atoms must be arranged differently. So they have the same atomic masses because they're all phosphorus. They all have the same ionization energies, which, by the way, is the energy it takes to pull an electron away. They all have the same nuclear charges, which, by the way, is the proton number. Right? The charge in the nucleus. So all of these things would be the same, 1, 3, and 4. But their molecular structure would be different if their properties are different. So 9 is 2. By the way, in previous tests, they would give you something like O2 and ozone. They say, why do these have different properties? Because they have different structures. They're both made of pure oxygen, but they have different properties. How about this one? Here's the chemical formula of diamond. Here's the chemical form of graphite. Of course, graphite is what's in your pencil, and diamond is something girls like to wear. Okay, some guys do. They have clearly different properties. Well, why? Different structures. Okay, number 10. Am I going too slow? I'm trying to teach all the background to each question.
You're doing good.
All right, thanks. You let me know. Given the balanced equation representing the reaction below, propane and oxygen, according to this equation, which ratio of oxygen to propane is correct? Well, be careful. Read it carefully. So, ratio of oxygen to propane. So, coefficients tell us the ratio of how many, not how heavy. So this means that every one of these, you need 5 of these to make 3 of these to make 4 of these. So, it's a ratio of how many. The question is, what the heck is propane? I have no idea. But propane, from organic chemistry, prop is a certain number of carbons. So let's go there. If you forget, we have a reference table for these organic compounds, and they're over here. And I think we have over here, prop is 3 carbons. So there it is. And they said propane. Go to table Q. We got the ethane here. So alkanes are single bonded. So having a prop means you have 3 carbons, and they're single bond because they're ane. Fill in the rest with the H's. So clearly my propane molecule is the first molecule there. Probably knew that. I'm over teaching. I get it. This is my propane. So oxygen to propane. That means I'm going to do the oxygen first. There's 5 of these to 1 of these. It's a 5-to-1 ratio. Now you may be tempted to do this one quickly. Remember, these numbers are not how heavy. It's how many. Right? We use moles. So it's 1 of these to 5 of these. It's got nothing to do with mass. Mass would not be a 1 to 5 because every atom has a unique atomic mass. So this is a how many number. So it's going to be 5 moles of O2 to 1 mole. That's a 5-to-1 ratio. Now, reasons why it's 5 over 1, because the oxygen goes first. If they said propane to oxygen, that'd be 1 to 5. Of course, that's not listed. So choice 2 is the answer. If you make the W sound. I'm getting bored. All right, I don't know. English is a weird. Yeah, okay. As I'm abusing the language here. Okay, number 11. Lithium and potassium have similar chemical properties because atoms of both elements have the what? If you're similar, I can't say this enough. If you're similar chemical properties, it's because you have the same valence electrons. This is something they love to ask. So you must be in the same column or family. My friends in chemistry, we call families, or we know that families are related. They look the same. They react the same. What makes chemical families the same is the same valence electrons. They react the same. So it's the number of valence electrons. That's one you just have to know. But you could remind yourself, okay, if you go to the reference table here, maybe, and we go here, and let's look at the alkali metals. You should know the alkali metals are the group 1. What makes these guys similar is they all, if we could just make this bigger, they all have 1 valence electron. They're in group 1. If they have 1 valence electron, they tend to lose it, which means they all become +1. So if you're writing a chemical formula like XCl, and they say, hey, which group on the periodic table could be the X? Well, if chlorine has to be -1, and I know that because when I look at chlorine, I see that it becomes -1. All right here. Has to be negative because the metal has to be positive. Then the X has got to be +1. Well, who is going to be +1? Guess what? Lithium, sodium, potassium, all of these will bond in a similar fashion. That's why it works. I know I'm over teaching it, sorry. Okay, so 11 is definitely going to be 4. All right, clearly the same. Now they can ask you that on a test and say which elements are the same column, okay? All right, number 12. Which 2 substances are covalent compounds? Now, covalent compounds, you have to know, are compounds where you're forced to share electrons. I always say forced to share. Now, why do I say forced to share? Well, I do that because, let's get rid of some things here so we can make some room. I say that because if you're covalent, you must be sharing electrons. Now there's two basic ways we bond. We transfer electrons or we share them. Case in point. If I have sodium, who has 1 valence electron, and I have chlorine, who's got 7, for reasons we should know already. The electronegativity of this is 0.9. That's the attraction it has for electrons. It's a metal. It's bigger. Electrons are farther away. They lose them. They don't have attraction for electrons. Nonmetals are smaller. These guys have larger attraction. I believe it's 3.2. Okay, now, because the difference in electronegativity is so great, this guy attracts him so much more sodium, this one takes it. And what happens to chlorine? Well, chlorine becomes Cl with now 8 dots, like a noble gas, and becomes -1. Sodium lost its valence electron, no dots left, and is +1. And they stick together because a positive ion attracts a negative ion. We call it ionic. So we know metals and nonmetals create this scenario. But wait, what if both elements have high attractions? For instance, what if I had hydrogen, who is 2.2, electronegativity, pretty high. And let's say I've got chlorine again, which I'm guessing is 3.2. Again, well, chlorine still has its 7 valence electrons. I'll draw these dots bigger. And hydrogen has its 1. Well, there's not going to be a transfer here. The difference in electronegativity is not as great. Chlorine cannot pull this away. So all it can do is what? Be forced to share. So this one, oops, not that one. So it's forced to share the pair of electrons. So by sharing, chlorine feels like it has that 8, and by sharing, hydrogen feels like it has 2. Now, of course, hydrogen wants 2 because 2 electrons fill its first energy level. So what am I looking for? Covalent bonds are sharing, and it must be between 2 or more nonmetals that have similar electronegativity. So you should be able to recognize that this is a nonmetallic compound called a molecular substance. They make molecules. But Ki is a metal nonmetal. That's ionic. Right. This is covalently bonded. Carbon, hydrogen, oxygen are nonmetals, and hydrogen, chlorines are nonmetals. So all nonmetals, there's your winner. 3 is all ionic compounds. Metal. Sodium's a metal. All right, so that's all ionic. Right. And then this is ionic here, and this is covalent. So the best answer is 2. Now, understand, they could have said the same question and used the word molecular. Now, molecular compounds are covalent compounds, so it'd be the same thing. And you need to understand that a molecular compound is covalent. Why? Because covalent compounds make molecules, whereas ionic compounds do not. They make crystals, crystal lattices. Okay.
So if covalent are forced to share, so non-covalent are not forced to share?
Right. In the case of the ionic that I have here, all right, because the difference in electronegativity was so high, there was a transfer. Metals are big, electrons are farther away. Their attraction for electrons, called electronegativity, electronegativity is a fancy word for attraction for electrons, is low because they're big. These guys, electrons are really held tightly, so this guy just pulls them away because the difference is high. But the difference is very similar. Think of me and my 4-year-old son. We have a tug of war. If I was serious about it, I would pull a rope right away from him because I'm so much stronger. I'd be like the nonmetal with a high electronegativity, high attraction for the rope, which is the pair of electrons, or its electrons. Here, if me and my brother have a tug of war, we're both similarly strong. He might, or I might be a little bit stronger, but not strong enough to pull the rope away, so we're forced to share the rope to be stable. And we can get stable by sharing. However, you should recognize, though, the one who is stronger pulls the rope closer. Notice I have this pair pulled closer to the chlorine. This is called a polar bond because you're sharing unequally. This side of the bond is polar because it's got more electrons. All right? And this side would be positive. And the greater the polarity, they could ask you, who has a more polar bond? The greater the difference in electronegativity, the more this gets pulled closer and makes this side of the bond more negative. Not molecule, just bond. And if this was H and H or Cl and Cl, you'd be sharing right down the middle. Right. They call that a nonpolar covalent bond. Okay? All right. So as we continue here, all right. So number 14. Oh, I think I skipped one. Yeah, I think I whited out something. Yeah, I do that a lot. All right. So here we go. Oh, let's erase that. All right. So I know I gave you a lot more than you needed to do that there, metal, non-metal, non-metal, but it's the background stuff that you need to have with you. Okay. All right. So number 13, when substance dissolved in water forms a solution that conducts electrical current. You know, they can ask this an entirely different way. They can say, which of the following choices is an electrolyte? That's what they're really asking. In solution, if you conduct electricity, you're an electrolyte. And you need to understand, as everyone does, to conduct electricity in a solution, Christmas in July here, you need to have free ions. It's important you understand, to conduct electricity in solution, ions have to be free to move. Now, if you look at your choices, and I'll scroll down here, what we're looking for is something that breaks apart into free ions. And I'll just try that. Okay, now, let me just white out the bottom so I can make a list here. Now, who makes free ions? Well, you should know things that make up ions are ionic. We just talked about that in the last question. So we will say salts are a fancy word for ionic compound. Salts are electrolytes, right? Because they're what? They're ionic. They're made of what? Ions. They're ionic. Think of an ionic compound. Think of sodium chloride. You know how I think about sodium chloride? In my mind, I think this. A positive sticking to a negative. So, of course, in water, these guys will break apart into their ions if they're soluble. So really, it's soluble salts. 2, acids. What do acids do? Well, look, HCl, even though that this is covalently bonded, acids are special because they'll break apart into the proton and the conjugate base, which, my friend, that's ions. And also what? Bases. Now, there's many types, but some bases, like NaOH, dissociate into, guess what? Na plus and OH minus. These are also free ions. So I'm looking for a choice that's either an ionic compound, a salt, a metal, non-metal, an acid, or base. Now, if I peruse my choices, I notice that carbon, hydrogen, and oxygen is in all of these. So these are all non-metals. So these look all covalent. So I'm befuddled here. There's no salts whatsoever. There's no metal, non-metal, metal, polyatomic ion, nothing. But I should realize that there is an acid here, or a base. Now you say, well, what's a base? Well, bases have OHs. Well, this is not a base. This is an alcohol. Right. People, they love to put alcohols in these questions for you to pick. Oh, if it's got an OH, it's a base. No, table R, this hydrocarbon with an OH tells you it's an alcohol. It's not a base. In fact, in some small circles, they consider it to be slightly acidic, but that's not for this course at all. This is covalent with nothing. This is another covalent compound that doesn't break apart. But what do we know about the Cu group? My friends in chemistry, in table R, this is an organic acid. If you are clueless about this, always pick the Cu group because it's different. All right? Now, if you didn't know where to look, if you didn't know COOH was organic, then we go to the reference tables, and you have table R is your friend here. And here is table R in all of its glory. You can see that the alcohol is not an OH. When you see the OH here, it's bonded covalently. It's not an ion that breaks apart, so it's not the one we want. But the organic acid, where they get the Cu group from is it's a C, and they got what? 2 O's and an H right here, an organic acid. And acids dissociate into ions. So that's how that works. Okay? Now, if you're not really sure about that, this CH3 COOH dissociates into this and an H+. These are ions. Okay? So that's that. So that obviously 13 is choice 4. It's an acid. Acids break apart into free ions in solution. So number 13 is choice 4. The acid is an electrolyte. They didn't say the word electrolyte, but they were basically saying it by their definition. All right, 14. Now I'm looking at this. Wow, a big atom is being split into smaller pieces. But which phrase best describes this reaction and its overall energy change that occurs? Well, I should be able at this point in our career understand that a slow-moving neutron is splitting this atom. Splitting an atom is not dealing with electrons. This is a nuclear reaction. It's not a chemical. Chemical reactions deal with electrons, either being what? Shared or transferred. Here we're dealing with the changes of a nucleus that gives off tremendous energy. Now you should know that a fission is what this is explaining. Even though they're not asking, this is nuclear fission. And fission describes splitting the atom. And it releases tremendous amount of energy. This is what the bombs dropped on Hiroshima and Nagasaki at the end of World War II. They were atomic bombs, fission bombs. And the reason why they give up tremendous amount of energy is that a little bit of the, binding energy, or a little bit of the mass in the atom was converted to energy. The binding energy here was unstable, too many protons, and you made what? Stable nuclei. So you're going from an unstable nucleus that could fission, give off radioactive particles, to stable nuclei, energy is released. And you should know fission is very exothermic, gives off tremendous energy. This is how we, of course, make energy in a lot of our power plants. Nuclear power is made by fission. So, any case, this question 14 is 1. Kind of an odd question here. Usually the nuclear questions are to the ends of the test. But, in any case, 15, you get these oddities in the January tests. 15, compared to phosphorus atom. You say atom, I say neutral. Atom, neutral, atom, neutral. Atoms are neutral. Knowing that, I know that the protons equal the electrons. So a P-3 ion, so an atom went from P0 to P-3. What happened here?
It lost electrons.
Okay. If I lost electron, what charge are electrons?
A negative.
Right. So if I lost negativity, wouldn't I be positive?
Yeah.
And losing electrons is what metals do. What's phosphorus?
It's gaining. Losing.
Well, let's think about this, right? What is phosphorus? We can use the periodic table to help us. Phosphorus is above the staircase. It is clearly a nonmetal. And by the way, as I mentioned before, metals are big. Their electrons are farther away from the nucleus. You can't find me a metal that becomes negative. All metals lose. So all metals lose electrons, which we call oxidation. Oops, not sure what happened just there. The oxidation. Nonmetals gain electrons. Remember the sodium lost the electron to the chlorine? So phosphorus gained 3 electrons. People get confused with this, but very simple. Start with phosphorus 0. That means it has 15 electrons, 15 protons. There's 0 because positive 15 in the nucleus and negative 15 outside the nucleus makes phosphorus 0. For it to be negative 3, it has to actually gain 3 negatives.
Right.
It doesn't lose protons because it wouldn't still be phosphorus. And why would it want 3 electrons? Because it has, how many valence electrons does it have?
5.
5. So it needs 1, 2, 3 to become stable. So nonmetals gain electrons because they're smaller, and it's easier to become stable. So this thing has 18 electrons, so it gains 3. Now if you don't like all of that background, you could have written a half reaction as well. All right? Don't use some opposite rule that help you. You always mess up. So look at this, P0 to P-3. the rule for half reactions is put the electrons so both sides have the same charge. So if I was to put plus 3 electrons here, okay, like you said, you originally lost, a -3 and a -3 is what? -6 on this side, and this is 0. Now charge must be conserved. So we need the 3 electrons to be over here. So it gained 3 electrons. All right, so P -3 has more electrons. Clearly, now, the question is, did they get bigger or smaller when they gain electrons?
They get bigger?
They do. Now, why? Help you remember that. Remember, go back to my reference table. Phosphorus has 15 electrons. 15 what? 15 protons. If you have 3 more electrons, now 18 electrons to the 15, the electrons outnumber the protons and they pull away. But if you don't like that, if you gain weight, what happens to you? You get bigger or smaller?
Bigger.
If you lose electrons or lose weight, you get
smaller.
Wait, one way to remember that. Okay? All right, moving forward and onward. Okay, so number 16. The balance equation below represents something.
Can we go over the radius part? I don't get the radius part.
Oh, okay, I'm sorry if I didn't answer the question. So more electrons and a larger radius. So when phosphorus becomes P -3, it has 3 more electrons. And we said phosphorus is atomic number 15. So it had 15 protons. And when it was atom, it had 15 electrons. Now, because protons are positive, electrons are negative, this gives me an overall 0. Now, in P -3, we still have 15 protons because it's still phosphorus. But now, to equal -3, we need 18 electrons. You have 3 more electrons than your atom. Now, if your nucleus is positive 15, and you were attracting 15 electrons, okay, the positive is attracting them. If you make the number now bigger to 18, don't the 18 electrons outnumber the protons?
Yeah.
So the electrons don't feel, or put it this way, the protons don't have enough charge to counterbalance the 3 extra ones, so these guys will move away a little bit. If you lose electrons, like metals, okay, you get smaller because the protons now outnumber the electrons and pull them in. In this case, because you are producing more electrons, the electrons are outnumbering the protons and they can pull away a little bit.
Okay. Yeah.
But if you get lost, very simple. You gain electrons, gaining weight, you get bigger.
Okay.
Losing electrons, losing weight, you get smaller.
All right.
One way to remember that.
That makes sense.
Don't put that as a reason on a test, but it's one way to remember it. Okay? 16. The balance equation shows bromine separating into 2 bromine atoms. What occurs? Okay, very classic question here. Clearly, we're breaking bonds. Because you have something bonded and now you have free atoms. So, bond is broken, correct?
Yeah.
Now, what you have to remember is, why do atoms bond to begin with? Like, for instance, why is bromine, who has 7 valence electrons, why is it bonded to another bromine who has 7 valence electrons? Why does it do that in the first place? What's the driving force? What's the reasoning? Well, they do so because by each one having 7, it's a good match. By them being forced to share, they both feel like they have 8. And as I said to you before, stable. You have to understand what stability means. Stability means low energy. So, they bond to become like noble gases to have low energy. So a bonded state is a stable state. It's a low energy state. Unbonded is a high energy state. They don't have an octet. To go from low energy to high, you have to absorb energy. Breaking a bond always requires energy because a bond is a stable low energy state. And making a bond, if this was a reverse, if you're creating a low energy state, these have high energy, this is low, it'd be exothermic. Now, if you forget that, after the review session today, let's go into town and break stuff. No, we wouldn't do that. But the point being is, if you want to break something, don't you need energy?
You do.
So that's what that's about. So yeah, bonded state is a stable state. It's low energy. They both have what? Octets. So you would need energy to what? Change a stable state. Remember Mr. Stable?
Yeah.
He's lying on the ground. He's not going to change his state unless you give him energy. Well, that's the same thing here. So energy is absorbed and a bond is broken. Choice 2. If it was written the reverse, it'd be energy is released and a bond is formed. Okay, but there we go. All right, moving forward. 17. Which substance can be decomposed by chemical means? Chemical means what? It means that you're breaking bonds. So you've got to have bonds to break them. So if you look at your choices, tungsten, if you go to table S, is an element. Antimony is an element. Krypton is an element. Hey, methane. Meth means 1 carbon. A means single bonds from table Q. Methane is a compound that has 4 bonds. You can break the carbon and H down into hydrogen and carbon. This is the only one that has bonds to break. That's why it's choice 4. I love this question. Number 18. Bronze contains 90 to 95% copper and 5 to 10% tin. Because these percentages can vary, bronze is classified as what? Well, look at methane, for example. Methane is CH4. It's a compound. It's 2 or more different elements. Compounds have an exact chemical formula. You can't just say, well, methane is CH4 today and tomorrow it's CH5. No, no, no. It's got to be exact chemical formula. There is no varying. But a mixture, you can vary. Hey, a salad is a mixture. You can have more tomatoes if you like or less tomatoes. You can have a dilute solution of sodium chloride or a concentrated. Mixtures are not chemically bonded. You can change and vary the conditions. So what they're getting at here is mixtures can be changed, can vary, but a compound or an element or a substance, my friends in chemistry, I shouldn't do this, but these are all, a substance is homogeneous, meaning they don't vary. Elements are the same because they're made up of the same what? Same atoms with the same number of protons. Compounds are made up of the same molecules. Okay, so clearly the mixture is 3. I shouldn't confuse it yellow. So the answer, of course, is a mixture. Number 19. Compared to a 2.0 molar aqueous solution of NaCl in a 1 atmosphere, 3 molar aqueous solution does what? Okay. What you should have learned is that as you add stuff to water, we have a 2 molar, this is a concentration, it tells us how much stuff is dissolved in water. We have an aqueous solution, which means we have sodium chloride dissolved in water. The 2 molar just tells me there's 2 moles for every 1 liter of solution dissolved. Now, as you add sodium chloride to water, it gets in the way of the water trying to boil and freeze. So the boiling is elevated and the freezing point is depressed. If you're making it hard, if you're getting in the way, then it takes more energy to boil. Think with me, I'm trying to boil, I'm trying to get to the surface, but these big sodium chloride ions are in my way. They make it tougher for me, so I need more energy to do so. If I'm trying to freeze, which means I'm trying to get in a crystal pattern, and stuff is in my way, I need a colder temperature to get that. So the way to remember this is this very, very, very important chemical symbol to get to the chemistry party. To get into the chemistry party tonight to study. It's this symbol. Or you do this. Alright? Just show this at the door. The higher temperature, the boiling is elevated, the lower temperature is depressed. So coolant and antifreeze are the same thing. Coolant prevents boiling because you add stuff to water, so it raises the boiling point so that you don't have boiling. Right. Antifreeze prevents freezing because it lowers the freezing point so much you need a colder temperature to freeze. So it does that. So you need a higher boiling point and a lower freezing point. And that is something that you just have to know. Okay, but hopefully that little thumb up and thumb down. As you can see, not a good artist. But I'm tall. Okay, so 19 is 4. Higher boiling point, lower freezing point. Number 20. Which reaction electrons transfer from one reactant to another? Hey, electrons are being passed around. Well, that must mean I'm dealing with a redox reaction. Right? Reduction means you're gaining electrons. Oxidation means you're losing. You transfer electrons. Someone's gaining, someone's losing. That's how a battery works. Electrons are going from the anode, the ox, to the cathode, the reduction. So one way you can do this is assign oxidation numbers to every single one of these choices. Or you could, you could actually just find yourself a 0. Where's a 0 in any of these? Now, a 0 means you have an element bonded to itself, or another element just hanging out.
Right. Oh, there's a 0 like above the O2.
Right. Boom. Answer. Looking for a redox reaction? Find yourself a 0. Why does that work? Because if it is a 0, that means it's something other than a 0. Right here it's -2, which means the oxidation numbers are what? Changing. Calcium is a 0, which means when it's bonded to something, it's something other than a 0. So all you have to do to identify the redox reaction is look for a standalone element, either bonded to itself. There's your redox reaction. The charges are changing because electrons are being passed around. 20 is 1. Which statement must be true for any chemical reaction at equilibrium? There's two things at equilibrium. Okay? And the way that I always remind myself is if I have 10 people on this line, and I have 2 people on this line. These are pictures of people. And if I make them cross lines, 1 person on each side every minute, the number of people will stay the same on both lines, wouldn't they?
Right. Yeah.
Why? Because the rate of the forward equals the rate of the reverse. Or the amount of each stay constant because of that. Let's look at the questions. The concentration of the products is greater. That doesn't tell us anything. Products is less. The products are equal. It's not about the concentrations. It's about them being what? Constant, because the rate of the forward equals the rate of the reverse. So that's why 21 is 4. 22. Oh, organic question. All right. What is the IUPAC name? Okay, so the first thing that I do is count carbons. 1, 2, 3, 4, 5 carbons. Now, I also have an ending here. Okay, so I have to go to my reference table. So I have, well, I don't need that, so I go to my reference tables, and let's go to the number of carbons first. And we go here. And number of 5 carbons is a pent, like a pentagon. So I have a pent. Now, were they single bonds?
Yes.
Yeah, they were single bonds between the carbon. Don't get lost and think that's a double bond. No, single bonds all between the carbons. Okay, between the carbons we look for. Now, because of that, table Q helps me out now, because single bonds between the carbons tell me it ends in ane. So far I've got a pentane. Pent for 5 carbons, and ane because of the single bonds. But there was some kind of structural formula or some kind of functional group. A C, now look at this. We have the rest of an organic compound. This could be an R, the rest of an organic compound, and then I have C, and I have this at the end. Let's go to table R to find that. So I go to table R at some point, and there it is. There's the rest of the organic compound and look what it ends up with. Oic acid. So now going to give me an example, a 3-carbon example there. So let's go back to the question. And I have pentane and then oic acid, choice 4. Pentanol would be the OH group on table R. Pentanal would have this group at the end, an aldehyde ending. And methylpentanoate's an ester. So the one that matches this ending is choice 4. Okay?
All right. Yeah. Got it.
Yeah, right off the tables. At one point you had to memorize all those. A few years back. Now they give them to you. Okay, unsaturated hydrocarbon. Here's the first thing that I see. Hydrocarbon. That's just hydrogen and carbon.
Right.
So I'm getting rid of 2 and 4 because they have oxygen. Now, saturated, they want unsaturated.
Saturated means when it has more than one bond, right?
Saturated means you're holding on to the maximum amount of H's possible for that carbon chain. So if you look at my 2 choices, 1 and 3, who's got the greatest number of H's per 2-carbon chain? That one.
No.
Why? It's saturated because it can't hold anymore. Why? Because carbon must make 1, 2, 3, 4 bonds. This carbon makes 1, 2, 3, 4 bonds. Every carbon must make 4 bonds. So I can't add an H here. This is the maximum amount. This one is not the maximum amount. Because of the double bond between the carbon, there's less H's. And having less means you're unsaturated. So this should have 6. This is what? This one is C2H6. This is C2H4. It's got less because of that double bond. So this is your unsaturated hydrocarbon. This is your saturated. So choice 3 is your answer. And table Q shows you that. They don't say unsaturated, but the ones that have the what? Greatest number of H's for the same carbon. By the way, let's go there for what the hey, since we're there anyway. Look at this right here. As we go down, this is our saturated one. These all have 2 carbons. What's happening to the amount of H's? They're becoming less as I add more bonds between the carbons. Look at the general formula. It's just 2N plus 2, 2N, 2N minus 2. You're losing H's. You're not saturated. You're under. So you got to have a double or a triple bond, and you call that unsaturated. Okay. Number 24. Which group of nuclear emissions is listed in order of increasing charge? Now, if you have no idea, table O is your friend here.